So chapter 3 is all about symbolic logic and proof. We reviewed this a little bit in chapter 0, but now we're just going to take a little bit of a deeper dive. Just so you guys know, I'm sitting on my porch and recording, so you're probably going to hear some birds and maybe some fireworks as the 4th of July is fast approaching. So the first section is all about propositional logic. So a proposition is simply a statement, and a statement is a declarative sentence that is either true or false. The key point is it's a declarative sentence. An example, Abraham Lincoln was the 16th president of the United States. That is true. The Blues won the Super Bowl. This is a declarative statement, but it is false because the Blues are a hockey team. Friendly reminder, no statement is both true and false, ignoring Schrodinger's cat. If you don't know what that is, Google it. Or Badu it. Yeah, that's what I had to do when I was in China. There I said, fireworks. So, some examples of non-statements. She is super cute. That's not a declarative sentence. Get your feet off the table. Is today Wednesday? This is a question. This is an instruction, right? So these are not declarative sentences. Propositional logic is used to study the way statements interact with each other. And we do this by finding compound statements. So a compound statement is formed by combining two statements using and, or, not, and, if, then. A simple statement is a statement that is not a compound statement. You might see this called an atomic statement and a molecular statement. Remember, molecules have multiple atoms. So here are our logical connectives. When writing compound statements in terms of the components of its parts, we use the logic symbols, and, or, not, this is also known as negation, and if then, this is also known as implication, which we talked about in chapter 0. So we are going to make truth tables to determine the values of our statements. So consider the sample statement P. It has one of the two truth values, okay? It's either true or false. And we can list all the values of P in this table. So P is either true or false. A truth table is a table that includes a column for each simple statement, a column for the compound statement, a row for each possible combination of truth values for the simplest statements, and a column for the statement form that has its truth value depending on the truth values of the simple statements in the corresponding row. So basically it fills out the compound statement. So let's look at some examples. So let's look at the truth table for not P. This is negation, okay? So if P is true, then not P is false. If P is false, then not P is true, okay? P has the opposite value of not P. And tables, in order for and truth value to be true, is only true if both my simple statements are true. So let's say I have the statement P and Q. This is also called a conjunction of P and Q. If P is true and Q is true, then P and Q is true. But if there's any combination of true and false, or they're both false, it's always going to be false. So there's only one way and can be true. This is the truth table for P or Q, right? This is called the disjunction. It's true if either P is true, Q is true, or they both are true, okay? I just need one or the other to be true. So if I have P is true and Q is true, P or Q is true. If I have P is true or Q is true, then P or Q is true. But if they're both false, then P or Q is false as well. Next, we'll look at the conditional connective. This is implication. The statement P implies Q is false if and only if P is true and Q is false. So, true implies true is true. True implies false is false. False implies true is true. And false implies false, that's true. So it's only false when we have a true P implying Q, which is false. So just so you know, PEMDAS, friendly reminder, PEMDAS is the order of operations, right? It's parentheses, exponents, multiplication, division, addition, subtraction. Well, we have that for logic as well, and it's called the order of precedence. Okay, so whenever two or more connectives are listed in a statement form with no parentheses, right? That would mean we couldn't indicate the order. This is the order to be used. So it's going to be negation, that's supposed to be a not, and, or, implication, or the biconditional. I came up with Noab. I was wondering if you could come up with a sentence to help remember this. I'd love to hear your input. An example is PEMDAS is please excuse my dear Aunt Sally. But I was wondering if we could come up with something for the order of precedence for logic. Be creative. So why don't we go ahead and insert parentheses into the statement to show the proper order for the application of the connectives. So let's go ahead and work through this order of precedence example. So remember, our order of precedence is Noab, which is not, and, or, implication, biconditional. So the first thing I want to do is I'm going to work with my negation. Now sometimes you'll see this represented with a tilde. This is actually not. So let's go ahead and put in our parentheses. The first thing I'm going to take care of is this negation. So I have negative x and r. So next I take care of my ands. Next I take care of or. And then last I take care of implications. There's a lot of parentheses in here, but they are necessary. The next thing I want to talk about is the biconditional. This is the statement written as P implies Q and Q implies P. It's referred to as the biconditional, which we write with this double arrow. And it's read P if and only if Q. You might also see that written IFF, that is like a shorthand for it in classes, like if and only if. The biconditional is true only if both statements of P and Q have the same truth value. Otherwise, the statement is false. So here I have my biconditional, okay? If they both have the same truth value for P implies Q, then we have that P if and only if Q is true. So let's go ahead and prove the biconditional. So let's look at this. P implies Q is true. P implies Q is false. False implies true is true, and false implies false is true. Now let's take a look at this again for Q. True implies true is true. False implies true is true. True implies false is false. And false implies false is true. So now I want to know and. This is only true if both of them are true. So I have true, true, false, false, which is the same as our implication for the biconditional. One thing I want us to get really good at is constructing truth tables. So why don't we work through some more examples? I have P, Q, P or Q, not P or Q. So first I'm going to have P is true, true, false, false. Q is true, false, true, false. And the reason I do this is to make sure I have every possible combination of true and false. P or Q is true, that's true. P or Q is true, that's true. False or true, that's true. False or false, that's false. Now I want to know not P or Q, so I need to take the negation of each of the values in this column. So I'd get false, 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 true. And for some of these, I've included the completed table in the PowerPoint, so you can use that as a review. Okay, let's construct another table. Let's construct this one. It's a little more complicated, right? So I have true, true, false, false, true, false, true, false. And I want to know not Q. Well, not Q is going to be the opposite of this column right here. So that gives me false, true, false, true. Now I have and. This is only true if both values are true. So I have and is true and false is false. True and true is true. False and false is false. And false and true is false. Now I'm taking the negation of this column. So now I have true, false, true, true. So now I want to know this column or P. Remember that or is true as long as one or the other is true. So here I have true and true, that's true. False and true, that's true. False and true, because I'm looking at this column over here, guys. False and true is true, and false and true is true. Okay, this is interesting, right? All my answers are true. This is a tautology. A tautology is a statement that has a true truth value regardless of the truth variables and the values that contain it. And we denote that with a little t. A contradiction would be a statement of the form that has all false values regardless of the variables before it, the variables. And that's what we would denote with a C. Here's the formal definition. Two molecular statements P and Q are logically equivalent provided P is true precisely when Q is true. Okay? That means that they have the same truth value under any assignment of truth values to their atomic parts. So here are two molecular statements. Here are their atomic parts. Okay? So we would say that these statements, P implies Q, and not P or Q, are logically equivalent because they have the same truth values. Let's go ahead and prove DeMorgan's laws that we learned about during set theory, which was a couple chapters ago, using truth tables. So I have true, false, nope, that's not what I want to do, right? We do true, true, false, false. You could have done it the other way, but let's do what we're used to. Not P is false, false, true, true. Not Q is false, true. False, true. Next time we'll look at not P or Q. So I need to look at P or Q and then take the negation of that. So P or Q is true, not P or Q is false. P or Q is true, not P or Q is false. P or Q is true, not P or Q is false. P or Q is false, not P or true, false is true. So next I want to look at not P and Q. That means I get false, 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 true, right? So this was DeMorgan's rule, right? Negation just switches an and to an or to an and vice versa, right? But now I can see I have a tautology because both of their truth values are the same. I also put this in here so you can prove it in the other direction. I'm going to leave that one up to you guys. Next, I'd like to discuss the logical equivalence of implications and disjunctions. So P implies Q is logically equivalent to not P or Q. For example, if a number was a multiple of 4, then it is even. A number is not a multiple of 4, or else it is even. And here's our lovely table right here. Double negation is not, and it's logically equivalent to P. You know, two wrongs don't make a right, but two negatives do make a positive, right? The negative of -1 is 1. So if I have, it's not the case that I'm not going to the party, that means you're actually going to the party. So feel free to think about this mathematically or in sentence structure. It's up to you. But here we have our truth table for not P. The negation of an implication is a conjunction, okay? Not P implies Q is logically equivalent to P and not Q. That is the only way for an implication to be false is for the hypothesis to be true and the conclusion to be false. Next, I'm going to talk about deduction. An argument is valid if the premises and conclusions are related to each other in the right way, so that if the premises are true, then the conclusion would have to be true as well. So let's examine the following statement. If Edith eats her vegetables, then she can have a cookie. Edith ate her vegetables, therefore Edith gets a cookie. So I say this is a valid argument, right? It makes sense if we're thinking through it as a sentence language-wise, right? She eats her vegetables, she gets a cookie. She ate her vegetables, therefore she gets a cookie. But how do I definitely know this is valid? We can show this using deduction. So let's let P denote Edith ate her vegetables and Q denote Edith can have a cookie. Let's change colors. So I have if Edith eats her vegetables, then she can have a cookie. That's an implication. That's P implies Q. Edith ate her vegetables, so that's P. Therefore, Q. This is an example of a deduction rule, an argument which is always valued. This particular deduction rule is called modus ponens. So let's identify a valid argument using truth tables. So let's show that P implies Q, not P implies Q, therefore Q. So I have true, true, false, false, true, false, true, false. P implies Q is true, false, true, true, not P, false, false, true, true. Not P implies Q, false implies true, that's true. False implies false, that's true. True implies true, that's true. And true implies false, that's false. So now we look at the rows where P implies Q and not P implies Q. What's the truth value of Q for those where they're both true? It's going to be T. So Q has to be true. Here's a list of some equivalence laws other than modus ponens. You can prove any of these with truth tables. We've got double negation, which we showed, commutative laws, which is here, associative, distributive. These are some identity laws, where C and T stand for tautology, and contradiction, contrapositive, and equivalence. So here are these for you guys to enjoy. If you have any questions, please reach out and send me an email. I know this is kind of a shorter chapter, but it's really important that you get really comfortable making truth tables.